So let's kick off. So you all know the notorious proverb, data is the new oil. However, oil is by many means an outdated energy form, and although the analogy of polluting a non-clean material will still be relevant for organizations that have not yet successfully executed their data strategy, this analogy will still be relevant. But I would argue that for many modern companies, which is centralized around data and technology, data is more like water. You know, you can find it everywhere, and it's pure and clean, and it sort of feels like you have data on tap. So that's how life is as a data expert at Telenor Connexion. My name is Bresell, and I'm head of data. We at Telenor Connexion, we are processing almost 1 billion real-time events per day, and in addition to that, a few 100 million batch events. So these events are produced by machines, and they are following protocols. So it's almost feel like we have data on tap, and it's quite high quality, even though following protocols can be hard sometimes. It's in general, it works very well. So my team and I are very fortunate to work with the things that we love, and we love working with high quality data and delivering really actionable insights. And by doing so, we deliver a massive positive impact to colleagues at our company, to our customers, and also those owners that we have in owning our company. So the title of my talk today is Automated Machine Learning for Incident Management in Global IoT Communication. But I will start with a few slides from our marketing department, and not only because I'm proud of our company, but maybe more because they build up sort of this sort of story I will tell you today. So Telenor and Internet of Things, we are ranked top 3 in the world, Europe, top 10 in the world. We have more than 17 million IoT connections, and we have active devices in more than 190 countries. And we are the outstanding leader in the Nordic countries. And we have a lot of known brands that are trusted, we are trusted by delivering connectivity to. So Volvo Cars is one of those. Also the buses, trucks, and construction equipment from Volvo, Hitachi construction machinery, Husqvarna, the lawn movers, and Verisure home alarms. Also the wastewater pumps delivered by Xylem. We have Scania buses and trucks, and one of few super sports cars. And interestingly, the other day I found that Carpigiani they are providing ice cream machines, or the ice cream display machines. And if you go to IKEA and buy this 5 krona ice cream, it's actually a Carpigiani machine. So we have all sorts of customers, from healthcare up to heavy machinery. So why do customers actually choose us? And of course, we provide solutions that work at scale, but I guess that the two things that stands out is sort of our long experience of IoT, the Scandinavian heritage, and maybe most important, our excellent IoT experts at the customer support center that is online 24/7, 365 days a year to help and resolve any problems we have with the connectivity. So we are top ranked among all our peers, and we want to stay there. And being preferred by a customer is not something you should take for granted. We all need to evolve over time to over-deliver on the expectations, and it's hard, of course, but it's sort of something you should always strive for, and it's also a continuous journey because the expectations are always increasing. So it's time to understand what kind of role we actually play, and we provide global connectivity for our customers' devices. But I can assure there is no operator out there that actually have a global network, and not at least if you talk about mobile networks, because mobile networks are issued by licenses from a national agency. So mobile networks are either national or regional. So what kind of role do we then play? Well, if you look at the end-to-end communication for IoT, you will see you have the thing located somewhere in the world attaching to a local mobile network. That local mobile network needs, of course, to check with our core network to make sure that it's allowed to connect there. Once we have a connection and the thing needs to communicate, we route all the data back to the customer's data center in a secure way so it doesn't traverse the open internet and can be hacked. Customer can then, of course, also communicate to end users, either with the business user application, if it's an operational focused application, or it's a end consumer in terms of a mobile app or something. So the thing and the thing on the right side here is the customer's responsibility, meaning that the things in between is our responsibility. So when things go wrong and there is an incident, it can be on the thing side. It can also be on the local roaming network, or in our core parts of the system, the centralized part, or on the customer data center or IoT backend of the customer side. So we don't really know where things go wrong, but the problem here is that we only actually have control over this part. So meaning whenever there's something happening, we need to know when there is an incident, where it is, and why. And only then we can drive the resolution of it together with the roaming partners or the customers. And that team in Connexion that is responsible for doing all this is our Service Operations Center. So let's then deep dive into some architectures to understand what kind of data we actually work with. So again, you will see this is a rather old architecture, so I will start from what we actually came from. But at the bottom, you'll see the same thing that we saw on the other slide, is that we have the green thing and the car, the IoT thing that on the left side is actually belonging to a customer, and it's now roaming in the local roaming network. The roaming network then interacts with our core network, and we secure the connection to the IoT backend through a dedicated VPN connection. So all communication from the thing over to the customer is all encrypted. It's encrypted in the roaming network, it's encrypted between the roaming network and our networks, and between our networks and the customer's backend. So do we listen to all the sensor values and configurational changes that are pushed down to the thing? No, we can't actually see that. We cannot listen, we cannot analyze and capture the payload data. It's encrypted. But what we can capture is the control plane events. So whenever a thing tries to attach to a roaming network, we will get the request back home to us and see, does this thing actually allow to connect to this network? Is it included is this network included in the SIM card's roaming profile? If not, it will send an error code back saying roaming not allowed. But if it's okay, it will attach to the network and then ask for setting up a data session, meaning that we now have a data link between the thing and the IoT backend on the right-hand side. And that is something, that's an additional request that comes through that we can capture. So we know the timestamp and what the thing wanted to do, setting up a data session. How long is the data session? How much data is going up forth and back, and any kinds of error codes that captured. So this is kind of the handshake control plane information, and that is what we capture. We capture this in real time and stream it up to our cloud environment, where these are the ones and zeros, because it's actually binary encoded data. We decode that and enrich it. So a SIM card has a SIM card identifier. We need to link that to which customer it actually belongs to, and also what probe event of this data point actually comes from which operator. So that is then all ingested. In this previous solution, we ingested everything into our analytics data warehouse. And why did we do that? Well, we didn't really have a requirement to be super real time. We had only the near real time. So any 5-10 minutes delay was acceptable, and we will nevertheless measure things on an aggregated level, because we had so many different possible things that need to be monitored. So it was thousands of customers and many hundreds of networks. Okay, so we ingested all the data into the analytics data warehouse, and we then deployed or adopted a standardized business intelligence visualization tool that you see on the right, and run just simple SQL queries with some fairly standardized statistical tests, and see that what the most recent values is compared to the history. And if it still looks normal, we will color the code. The country will be colored green to indicate normal, but a country that has an anomaly in it will be turning red. So now you'll see that the Service Operations Center here will be able to look at this big screen in their on the wall and detect when a country is turning red. So when it's red, they will then need to do something. So it will go to the desktop application and look at that country and analyze and make and diagnose and conclude what actions need to be taken and take those actions, initiate a communication with the roaming partner or the customer. So I'm pretty sure that we were very proud of this and we thought it was super great, this solution. We ran it for quite many years, I would say. Back in 2015, we started with this. But we realized it had some flaws. And one thing was that this big screen monitor, it only showed the current state. So what does that mean? Well, when an employee in the service operations center starts the day and the shift, they will look at the screen and see a red country. Okay, how long has that country been red? Don't really know. They need to ask someone else. If they see a red country and need to go to lunch break and they come back, and they remember there was a red country in the center of Europe, and they come back and they still see a country that is red in Central Europe, but is it the same country? It's really hard to know. So all this was kind of issues that actually prevented the team to act effectively. One more problem is that there are always multiple persons working in the service operations center. So 24/7, there are different persons working different times, but at any given time, there are multiple persons working and addressing all these cases. So when they all look at the same screen and then taking individual actions to follow up, how do they know who is working on which case and who is working with which anomaly? So that has a lot of different complications also. So it not fully flied and addressed the actual business need that we had, but we thought it did. So we went back to the drawing table maybe 1.5, 2 years ago and started to build something, and we shipped it 1 year ago, and it looks something like this. It's very, very similar, but we moved the anomaly detection from consuming from the data warehouse to the real-time stream. And the reason we could do that was that we went out and looked for different model types that would address our case. And we found one called random cut forest that worked really well on our time series data. And we also discovered that there is a service where this algorithm was implemented in the service. So we had a real-time processing service that could adopt this model directly in it. So if we did this, we thought that we could actually avoid a lot of the operational load because it will all be production ready and automatic. So let's try it out. So in the stream, we keep like 1 week of buffered data, so it can learn from that history and constantly train from that buffer data. And then we always have new aggregates, and we produce features in this real-time stream, like aggregates or metrics or constructed metrics, and those are the ones that also the historical data is producing. So now the model can train on that and produce an anomaly score. So the anomaly score then is fed to a real rule engine, and if the score, of course, is above a certain threshold, it will take this information about the anomaly and all the observed data and move it into an alarm management tool. So one thing that actually was the key to change here is what that the service operation persons was not longer responsible for detecting and recording the anomalies. We moved that down to the AI machine learning machinery. The second thing that we did was that this alarm management tool now could keep states of an alarm. So whenever there was new information, new data about the same anomaly, we updated the score, we updated the last observed amount of transactions, etc. So we constantly fed and updated this information. And in case then when the users in the service operations center need to analyze this alarm management alarm, they had all these nice drill downs to figure out if it's if the anomaly is related to just one customer or is general to all customers, but just one network or something. And then we can easily isolate where the problem is, and we could deep dive into all the error codes, etc., and conclude on what the actual issue is. and then reach out to the counterpart in roaming partner or customer to resolve the incident. But the way we did it was that we did not feed this into our standardized incident management system by default. We had this pre-filtering working in the alarm management tool, because this machine, I mean, 1 billion events per day, and I think we produce, I don't want to say, but maybe a couple of hundred anomalies per day, and that's quite massive amounts of data. And if there is a huge disturbance, it will just ship all these anomalies into our incident management flow, which is Salesforce, and we didn't want that. So we kept this intermediate system to filter, and only those that actually required action, we marked a small checkbox and push a button, and then you can send a request into the standardized Salesforce incident management flow with a link to the alarm management tool. So there we can do all the analysis and drill down and go back and see if there's any updates. And in Salesforce, we have information about the customer's contact details, preferred contact methodologies, or like channels. We had phone numbers and addresses to all the roaming partners, etc. So there we can coordinate and maintain the cases over time in a very, very nice way, but still supported and elevated by the use of machine learning. So it all worked really well, and we're super happy with this solution now, and it's been running for more than 1 year now. And in hindsight, what we actually learned was that, well, you need to be really cautious when you put your machine learning in to deployment. You really need to be careful in design it in a way so that you can elevate your business process, and not just think about supporting them. You need to actually do a step change and make them much more effective. So what we actually thought the job to be done was to find and present anomalies, because that was what the operations center persons asked for. So that we built a model and visual tool. But what we found out was that to track and analyze anomalies over time is equally important. For that, we needed a state machine. And on top of that, we had multiple users and multiple alarms, so we needed a user and alarm management solution on top of this. Only then we actually felt that we delivered on the promise of actually changing the amount of things we can work on and the intelligence around the actions that we actually was taken. So that was really good, and we were very happy about this. So the last part I want to talk about is the ML ops. So, I mean, what happens here in our solution? Well, it's the red box here. It's the real-time machine learning machinery here. And the job to be done is to ensure that the model is always up to date, okay? So traditionally today, I mean, we've come quite far. The general approach is to task your data scientist to continuously train and optimize the model. But also to have your data engineers to build and maintain the machine learning pipeline, so you can always push out new models, updated and retrain models, etc., etc. So what's wrong with this? It's not wrong. It's not wrong. There's one caveat though, that it still requires quite many man hours, not just only for researching and developing, but also to maintain these over time. So that man hours are typical resources that are quite scarce. So it might block you from doing additional machine learning models and do more intelligent data solutions. So acknowledging that going to production is hard, and following the typical workflow, you look at your use case and look at the constraints it has. In our case, it was detecting anomalies in multiple different protocols. Then we looked at sort of what are the different models out there that will serve our purpose, and we found a few, and they all have some constraints in terms of they require time series data, or they need some pre-processing, whatever. But there's also some training constraints. Maybe you don't have infinite number of infrastructure that you can use, or you just have limited kind of data or something like that. But these are all the things that the data scientists and data engineers can work around. It doesn't block you, but something that I think is blocking a lot of companies out there and organizations that actually going to production comes with a lot of constraints. So moving something into production requires normally to follow IT policies, which might require that you do thorough testing of the software, and the software might include dependencies and libraries that are not scanned for vulnerabilities. And if you do that, you find that they are very old, and you need to update those, and you need to maintain those, and you need to go back and train them, and it's a lot of things to take care of. And just going to deployment might require you to schedule a service window, etc. And so it's quite complex exercise to go to production. And if you do this continuously, it makes it even harder. So there's a lot of operational constraints. And if you think of this and try to address these, because these will be the most kind of blockers that you will encounter, maybe that's the way to start. So one way to go about this, and the way we found, is that there is actually a service, a machine learning as a service from, in this case, about AWS, but many cloud vendors have these. You can also buy softwares or something like that runs it. But if you buy it as a service, you will have the infrastructure and the code, and everything around that will be maintained. So what does this imply? Well, it actually puts some constraints back to the model and training. You can't choose any model now, unless you use something like SageMaker or some generic framework. But if you use this as a dedicated machine learning as a service, you need to stick with the models they have. And there also, you can't load all your data there if you have a lot. So you need to there's some constraints around how much data it can actually cope with. So, but nevertheless, if you can accept these compromises and still deliver on your use case, well, then it can actually be, you have models that will be incremental, retrained and adjusted and maintained, and you have almost no ops, which is quite an important thing. So is this all a very good thing? No, it has some drawbacks, of course. And one of the things that we came across was that we wanted to produce quite many features, but we found that there was a limit of like 30 features, which we didn't have in open source counterpart. So we really need to think about and designing and evaluating and come up with really good features that worked for us under these limitations. The second thing that we found out was that when we wanted to replace a feature, it actually means that we need to retrain a model. So the models actually in production will be reset, because it's automatically retrained in production, and it's just incrementally adjusting it. But if you replace something as important as a complete feature, it will completely reset it. So it will be unstable. The score output will be unstable for maybe several hours or days in this case. So that's not ideal. But in our case, we worked very hard with the feature engineering, and once we settled that, we decided that it's not that important to change the features. They are working very well. And if you come to the point that you need to choose between a very accurate model or the ability to actually go to production, I will stress going to production is much more important. So so that was what was driving our sort of strategy here, and it paid out really well. I foresee that the accuracy model is enough. It could be better, but it's enough to actually serve a lot of value into this solution. So what I'm trying to say here is that if there is alternative ways to approach this, and if you start from the back or at the end in your deployment and operational part and work yourself backwards to see of all these options you can take when you're working yourself backwards, will it still address your use case? Then you're on a really good spot. So that's more or less it. I will wrap up with some key takeaways. One thing is that the detection and the output of model is not everything. Even though the model is super good, you need to think about the effective action. Those are the important. That is where you will have the scale-out effects, the return of investment, the step change of the performance, the change in customer experience. Okay, so think about that. It might require you to actually move ahead quite much in software engineering, front-end, user experience, etc., to actually address this. So going to production is hard, and then my advice is to only spend time on things you can actually deploy. rather than thinking of developing 10 models where which one model can go to the production because of technical limitations or policies, etc. So I also advise you to look into the machine learning as a service. They have some drawbacks in terms of freedom, etc. But if they fit your use case, it will address a lot of the technical and operational blockers and will free up so much user resources. So and that in itself can leave you up to have time to do further innovations, etc. So I think this is definitely something you should consider. Then the last advice was to start at the end. Make sure that you can go to production and work yourself backwards. That is probably it might be a really fast way to scale out your success because you're only working on the things that you can deploy. So that was my last words, and I'm now opening up for some questions if there are any. I don't think, yeah. Thank you very much for everyone that listened in, and those who want to stay for the question sessions will put tuned. The rest, I would wish a great rest of the day. Okay. So I have one question here from Sean. Anders, IT operations can suffer from the overall overload of red alert problem. Too much noise and not enough signal. Did this project reduce noise or boost signal or both? I would just say both. We increased the amount of things that we monitored. We produced a lot of anomalies, but we found out a good level empirically by tuning the cutoff. And as the model was better than before, the accuracy of it was much better. So I think we actually went for a very pragmatic approach where we set the cutoff at a decent level what the service operations center actually could manage. And in that it would include quite a bunch of false positives, but they could manage it. And rather than finding those very odd, obscure cases with a lower score, but producing too much false positives that they couldn't manage. So that's a good question, and I hope you understand. So it was a combination. We did reduce the noise, but we also boosted signaling, and it was a problem with the red alert problem for. Yeah. And do we have any more questions out there? Okay. Meanwhile, if there is anyone coming in more questions, I can advise you. I have actually, this is the 4th time I'm presenting at Nordic Data Science and Machine Learning Summit, and all these presentations I have here actually ties together in a very nice lecturing series. It builds on each other. So listening to all of them, you'll get a very good picture of our journey. So that's my advice. And if there is no other questions, and I will thank you very much for listening in, and I wish you a great rest of the day. Thank you.